Hello everyone, my name is Zhang. Today I'll be presenting our work, FusionFS, fusing L operations using CISCOps in firmware file system. This work is done in cooperation with Yujie and Sudarsun Kannan. Yujie and I contribute equally on this work. Nowadays, modern storage devices have entered into microsecond era, and in-storage compute is becoming more powerful. Meanwhile, fast user-level file systems have emerged to bypass the OS for reducing software overheads. Unfortunately, dominating our overheads like data copy, system core, PCIe communication cores remain. Most importantly, current solution lacks support for leveraging in-storage compute for I/O and data processing operations. To solve the issues, we propose FusionFS. First, FusionFS aggregates multiple identical and non-identical I/O operations into one single op, which we call CISCOps. Second, FusionFS fuses and offloads data processing operations in CISCOps to the storage device. Third, FusionFS introduced in-storage resource management for the fairness and explodes in-storage compute for fine-grained crash consistency. Overall, CISCOps reduced error overheads and achieves up to 2 to 4 times higher throughput. Now let's understand storage hardware trends. Modern storage devices are becoming more and more powerful. With more than 8 cores CPU and considerable DRAM, the high error cost between the host and storage device dominates the software overheads, and we aim to focus on how to use in-storage compute to remove those bottlenecks. Now let me provide a background on different file system storage approaches. In traditional kernel file system, the OS manages both data and metadata operations. For user-level file system, it disaggregates data plane operation and control plane operation, where data plane operation bypass the OS. Device file system takes a radical approach that offloads the majority of file system components to storage to provide direct access. At the end, compute offloading system can offload some specific tasks, for example, compression and checksum to the storage, but the file system remains in the kernel. Next, to understand application I/O access sequences, there are several common I/O sequences in application code. Firstly, simple I/O operations to store or read the state, for example, write or read. Secondly, the sequences of I/O operations, for example, open, write, read, write, close. Lastly, operations coupled with data processing operation, for example, append, checksum, write. Overall, reducing I/O overheads across all the I/O sequences is critical. Now let's go to the motivation part. First, let's look at common I/O sequences, read, modify, write, which will read a 4 KB block, modify it, and write it back. Kernel-FS need to read it from the storage to the kernel, and then copy the data from kernel space to user space, modify the data in the application, then write it back to storage. This requires 2 system core, 2 PCIe costs, 4 data copies. Another example is append, checksum, write, which needs to append the data block to storage and does the checksum calculation on the host, and then writes the checksum data back, which also requires 2 system core, 2 PCIe cost, and 4 data copy, and the data processing is in the host. Beyond the previous example, we have also analyzed read, modify, write sequences for all file system types. For kernel-FS and compute offloading system, it suffers additional system core overheads. For user-FS and device file system, which can provide direct access, but they can't avoid high I/O overheads. Similarly, for append, checksum, write, all of them suffers high PCIe cost and data copies overheads, and do not utilize in-storage compute for data processing. Only compute offloading system can provide checksum operations to utilize device CPUs. As we can see, none of the storage design except FusionFS can reduce high I/O costs between the host and storage, and also provide the ability for in-storage computing and effective device resource management. To solve the limitations of current software storage systems, we propose FusionFS. FusionFS aggregates I/O and data processing sequences into CISCOPs, which was inspired by CISC RSA. And FusionFS uploads CISCOPs to reduce I/O overheads. In addition to that, FusionFS provides a CFS-L scheduler to manage in-storage resources for fairness and performance efficiency across multiple tenants. In the end, FusionFS explodes storage compute for fine-grained crash consistency and faster recovery. To begin with, let me first introduce two widely used RSA, RISC and CISC. So here are the key differences between two RSA. For RISC, it has more simple instructions. In contrast, CISC has fewer and richer instructions composed of simple instructions. Since each of these two technologies has its own strengths and limitations, the debate about them has never stopped. Our goal is not to get into that debate, but rather explore RISC and CISC-styled I/O and data processing operations to reduce dominant I/O overheads. In FusionFS, RISC operations are simple POSIX I/O operations, for example, read and write. And CISC operations are aggregated I/O and data processing operation, for example, append, checksum, write. But unlike POSIX I/O vector, CISCOPS combines identical and non-identical I/O and data processing operations and offload it to storage. And according to our evaluation, CISCOPS can significantly reduce dominant I/O overheads. Now let's look at an example, append, checksum, write. For kernel-FS, it needs to write the data from user space to the kernel space and copy it back to the storage. It must do checksum in the application by using the host CPU. Finally, write the checksum data back. Therefore, it incurs high numbers of data copy, system core, and PCIe cost. But for CISCOP, we compound, append, checksum, and write to a single CISCOP and offload it to the storage device. So this only requires one data copy and one PCIe cost with direct access and offload computing. Next, let me describe the components in FusionFS. In FusionFS, userlib is responsible for converting POSIX I/O syscore to CISC I/O ops and adding I/O requests to the I/O queue. The OS is responsible for handling file system initialized setup. Finally, StorageFS handles both I/O and data processing requests and also provides CFS-L scheduling and fine-grained journaling. Here is an example of FusionFS-L processing. There are two threads. Each thread issues different CISCOPs. Userlib creates two anode queues and insert L commands to anode queues. Next, StorageFS will start fetching the queues from userlib. After succeeding in the credential check, the L scheduler will pick an anode queue and start executing it on the computer engine. In the end, fine-grained journaling can provide crash consistency. However, CISCOPS introduced two new challenges. First, how to provide fairness and efficiency across tenants. CISCOPS consumes more device compute memory resources than regular POSIX I/O operations. Therefore, it could impact simple I/O performance. Second, how to provide crash consistency for CISCOPS. We need to recover the internal computational state of CISCOPS after the crash happens. Therefore, FusionFS proposed in-storage CFS resource scheduling. It prioritizes anode queues with the least CPU usage, that is virtual CPU time, which is similar to OS CFS scheduler. Let's take a very simple example for this talk. We only issue CISCOPS to file 1 and simple ops to file 2. And let's assume only one CPU cores in device. And also, CISCOPS spend 5 times CPU cycles than simple POSIX operation. Also, StorageFS maintains a global red-black tree that stores references to the anode queues, which is sorted by virtual runtime. Initially, CPU cycles spent on each file is 0. First, FusionFS will pick anode Q1 and execute append CISC write. Meanwhile, update its corresponding virtual runtime. After that, red-black tree need to be rebalanced. Next, FusionFS will pick anode Q2 and execute the read operation. After that, FusionFS will pick anode Q2 again because anode Q2 has the least CPU usage. Therefore, CFS-L scheduler improved fairness across CISCOPS and regular POSIX-L operations. Now, the next question is how to provide crash consistency while packing multiple I/O and data processing operations in a CISCOP. FusionFS provides two crash consistency mechanisms. The first one is macro-transition, which can provide all or nothing approach. The second one is macro-transition, which can recover partially completed CISCOPS. Now let's look at how macro-transition works. Here is a simple example of append CRC write. First, FusionFS will add the transition begin log to the journal, and then add the log entry for append operation. After that, execute checksum on device CPU. Similarly, add the log entry for the write operation. At the end, commit entire transaction to the journal log, so that FusionFS can redo the journal log to recover the state. But the problem of macro-transition is how to recover the computational state when the machine crashed after the checksum finished, but the log entry are not committed to the journal. To solve this problem, FusionFS proposed macro-transition, which supports crash consistency of partially committed CISCOPS. For macro-transition, each operation can be committed independently. So, for append and checksum, FusionFS needs to update its corresponding commit bitmap. So after the machine crashed, macro-transition will check the uncommitted bitmap and then redo the operational log. So the checksum value can be found in the journal log. Due to time limitation, please find more interesting details in the paper. Now let's go to the evaluation part. Next, I will discuss the experimental setup to evaluate the FusionFS. We use dual socket 64 cores Xeon CPU and 512 GB NVMe as our storage. And due to the lack of no programmable storage, we emulate the firmware-level file system in the Linux kernel. And we compare the following state-of-the-art file system: kernel-level file system, ext4dex and Nova, user-level file system, SplitFS, firmware-level file system, CrossFS. The first evaluation goal is to understand the effectiveness of FusionFS and CISCOPS to reduce error overheads. First, we develop a macrobenchmark append checksum write. In this benchmark, each thread will first append a 4 KB data block and then do the checksum calculation and write the checksum data back. As we can see, ext4dex and Nova suffers high system core and data copy overheads. For SplitFS, it disaggregates data plane operation and control plane operation, but it still suffers high error overheads. For CrossFS, it has better concurrency compatibility, but it can't reduce data copy due to and lacks the support of data processing in storage. Therefore, FusionFS achieves 3.3 throughput than ext4dex. Similarly, for read modify write, we see the same performance gain. In addition to that, we applied CISCOPS on traditional kernel file system, ext4dex, to understand the effectiveness of CISCOPS. Even for kernel file system, CISCOPS also provide good performance. Next, we evaluate the Filebench with different workloads. For each workload, FusionFS will aggregate some common I/O sequences to one CISCOP. For example, open, write, close. In our evaluation result, FusionFS shows promising speed up with all the workloads. Now, we will study the macro-transaction durability and auto-recovery benefits. For recovery, we will run append checksum write with 16 threads and 16 MB I/O size. Also, we inject a crash of the checksum calculation. As we can see, FusionFS macro-transaction significantly reduce recovery time. Next, we evaluate the effectiveness of CFS-L scheduler. We will co-run two workloads. The first is append CRC write, and the second is L-intensive write-only workload. As we can see, CFS-L scheduler consequently improves throughput of write-only workload by 1.34 times, and only marginally reduced append checksum write throughput. At the end, we will show the real-world application performance. We evaluated LevelDB by replacing checksum logic with FusionFS CISCOps append CRC write. As we can see, FusionFS also shows high performance on LevelDB. To summarize, FusionFS is motivated by high I/O overhead and lacking support for leveraging in-storage compute. We propose FusionFS that fuse I/O and data processing operations into CISCOps and offload it to solve those issues. In addition, FusionFS provides a CFS-L scheduler for fairness, microtransaction to support crash consistency. To conclude, we believe it's critical to utilize storage resources to reduce I/O latency, and it's time for richer I/O abstraction that organically support data processing. Therefore, we take the first step towards richer I/O operations by using CISCOps. At the end, we observe efficient utilization of storage resources are critical for addressing durability and resource management challenges. Thanks for listening. Any questions?